Look up on a clear night and you'll see a few thousand stars. They look like they're pasted onto a black dome, all at the same distance, the ceiling of the world. For almost all of human history, we had no idea how far away they truly were. And here's the astonishing part. The woman who finally gave us the ruler to measure the universe was paid 30 cents an hour, forbidden to touch a telescope, and is still, today, largely forgotten. Her name was Henrietta Swan Leavitt. Working in a back room at Harvard, not even allowed to touch a telescope, she cracked one of the oldest problems in all of science. How do you measure the distance to something you can never reach, never touch, never travel to? Get it wrong, and you have no idea how big the universe is. Get it right, the way she did, and you unlock the size of everything. Keep that in mind, because by the end of this, one man will use her discovery to become world famous. Her name will almost vanish. It sounds simple. It is monstrously hard. You can't stretch a tape measure to a star. All you get is a point of light. A bright point could be a brilliant star far away or a dim star close by, and from just the light, you cannot tell which. Brightness alone is hopelessly ambiguous. There was exactly one method that worked, and it only reached the very nearest stars. It's called parallax. Hold up your thumb, close one eye, then the other. Your thumb appears to jump against the background. Nearby things shift more than far things. Astronomers use the same trick, with the Earth's orbit as the two eyes. As the Earth swings from one side of its orbit to the other, over 6 months, a nearby star appears to shift ever so slightly against the distant background. Measure that tiny shift, and geometry gives you the distance. It's beautiful, and it's real. But it fades fast. Because the farther the star, the smaller the shift, and it shrinks to nothing almost immediately. Parallax works for the closest few hundred stars, and then the wobble becomes too small to detect. Beyond that, the method goes blind. And the universe, it turns out, is unimaginably bigger than that. Past that little bubble lay the deepest mystery in astronomy. Those faint, fuzzy patches of light in the sky that astronomers called nebulae. Were they nearby clouds of gas within our own Milky Way? Or were they entire other galaxies, island universes, unthinkably far away? Nobody could say, because nobody could measure the distance. The whole scale of the cosmos hung on this question. Was the Milky Way the entire universe, or one island among billions? To settle it, astronomy needed a new kind of ruler, a way to measure distances far beyond parallax's tiny reach. It needed a standard candle. Here's the idea. Imagine you're on a dark plane, and scattered across it are candles, all identical, all the exact same true brightness. A near one looks bright, a far one looks dim. But because you know they're all really the same, you can use how dim each one looks to calculate exactly how far away it is. A known true brightness turns dimness into distance. So the dream was to find some kind of star whose true brightness you could know in advance, a cosmic standard candle. Find those, scattered through the universe, and you could finally measure the depths of space. But no such star was known. Finding one would take an extraordinary discovery made by an overlooked woman staring at photographic plates for 30 cents an hour. To understand her discovery, you have to understand her strange job. At the turn of the 20th century, the Harvard College Observatory was drowning in data. Thousands of photographic glass plates of the night sky, each dotted with countless stars, all needing to be measured and cataloged by hand. The observatory's director, Edward Pickering, hit on a solution that was equal parts practical and unjust. He hired women to do the painstaking measurement work because they were meticulous and because he could pay them a fraction of a man's wage. They were called, literally, computers. Human computers. There were dozens of them over the years, the Harvard computers, sometimes less kindly called Pickering's harem. They did the grinding, essential labor of astronomy, measuring the position and brightness of star after star after star after star, plate after plate, for years. Painstaking, brilliant work for about 30 cents an hour. And they worked under a hard ceiling. By the conventions of the day, this was women's work, cataloging and calculating. The prestigious jobs, the theorizing, and often the very telescopes themselves, were largely reserved for men. These women measured the heavens they were rarely permitted to observe directly. Yet, from this constrained, underpaid corner of science came some of the most important astronomical discoveries ever made. Several of these women changed our understanding of the cosmos forever, and none more profoundly than Henrietta Leavitt. Leavitt joined the observatory in 1902. She was a New England minister's daughter, Radcliffe, educated, brilliant, and, after an illness, increasingly deaf. She was quiet, devout, and utterly dedicated to her work. Pickering handed her a specific, tedious assignment to catalog variable stars. A variable star is one whose brightness changes over time. It brightens and dims, sometimes over days, sometimes over months. To find them, Leavitt compared photographic plates of the same patch of sky taken on different nights, hunting for the few dots that had changed. It was extraordinarily tedious, eye-straining work. She was breathtakingly good at it. Over her career, Henrietta Leavitt discovered more than 2,400 variable stars, about half of all those known in her lifetime. She had an almost supernatural eye for spotting the tiny, blinking changes buried in fields of thousands of stars. And she concentrated her attention on one particular region, two faint cloudy patches in the southern sky called the Magellanic Clouds. It was there, in a special kind of variable star, that she would find the key to the size of the universe. The special stars Leavitt was studying are called Cepheid variables, named after a prototype in the constellation Cepheus. And they are remarkable. A Cepheid doesn't flicker randomly, it pulses, physically swelling and shrinking, brightening and dimming on a strict, regular repeating cycle, as reliable as a heartbeat. If you chart a Cepheid's brightness over time, you get this distinctive shape, a swift rise to a peak, then a slower fade back down, over and over, with a period as precise as clockwork. Some Cepheids cycle in a couple of days, others take weeks or months. But each one keeps its own perfect time. Why do they pulse? Deep inside a Cepheid, a layer of gas acts like a valve. It traps heat, causing the star to expand. Expanding, it cools and becomes transparent, releasing the heat and letting the star fall back. Then it traps heat again. The star breathes, in and out, driven by its own physics. But Leavitt didn't need to know why. She just needed to watch them tick. And the Magellanic Clouds were the perfect place to watch, for one crucial, brilliant reason. Because the Magellanic Clouds are so far from us, all the stars within one of them are, for practical purposes, at essentially the same distance from Earth, like a distant crowd of people, all about the same distance down the road. This is the key that unlocks everything, so let's be clear about why. Normally, comparing the brightness of two stars is useless because you don't know their distances. A brighter looking one might just be closer. But if two stars are at the same distance, then whichever looks brighter genuinely is brighter. The distance ambiguity vanishes. So within the small Magellanic Cloud, Leavitt could do something no one could do for scattered stars. She could directly compare the true brightnesses of her Cepheids, just by comparing how they looked. The cloud was a natural laboratory, a shelf of stars all lined up at the same distance, waiting to be compared. Leavitt patiently measured Cepheid after Cepheid in the cloud, recording, for each one, two things: how long its pulsation cycle took, its period, and how bright it was. And as she assembled her table of periods and brightnesses, a pattern began to emerge from the numbers. A stunningly simple, orderly pattern. The brighter Cepheids had longer periods, the dimmer ones had shorter periods. And it wasn't a vague trend, it was a tight, precise relationship. The longer a Cepheid took to pulse, the brighter it truly was, in a clean, predictable way. Leavitt had found a law hidden in the stars. She first reported the hint of this in 1908, and then, in 1912, she nailed it down with 25 Cepheids. When she plotted the period of each star against its brightness, the points fell almost perfectly along a straight line. This is her discovery, one of the most consequential graphs in the history of science. Look at how clean it is. Tell me how long a Cepheid takes to pulse, and this line tells me its true intrinsic brightness. The period, which you can measure from anywhere, just by timing the star, reveals the luminosity. And that is exactly precisely the standard candle astronomy had been dreaming of. Do you see what this means? A Cepheid tells you its own true brightness, just by how fast it blinks. And once you know a star's true brightness, and you measure how dim it looks from Earth, the difference gives you its distance. Leavitt had turned a blinking star into a cosmic ruler. This was the breakthrough. For the first time, humanity had a way to measure distances far, far beyond the tiny reach of parallax. Anywhere you could spot a Cepheid, in distant star clusters, and other nebulae, you could now, in principle, measure how far away it was. The universe had suddenly become measurable. But Leavitt's discovery had one missing piece. She had found the relationship that longer period means brighter star. She could rank Cepheids and compare them, but to turn a Cepheid's period into an actual distance in light years, you needed to anchor the whole scale. To know the true distance to just one Cepheid, to calibrate the ruler. And here we hit the injustice at the heart of this story. Leavitt, who had made the discovery, was not permitted to develop it. She was a computer, assigned to measuring and cataloging. Pickering reassigned her to other duties, turning her relation into a working distance scale. The glory work was left to others. In 1913, the astronomer Edwin Hubble took the crucial step, using parallax measurements of a few nearby Cepheids to calibrate Leavitt's scale, to put the zero mark on her ruler. Now a Cepheid's period could be turned into a real absolute distance. The yardstick was complete, and it was about to be pointed at the deepest question in astronomy. Armed with Leavitt's Cepheids, astronomers now had a tape measure that could reach across staggering distances. And the person who would use it to shatter our picture of the universe was a young, ambitious astronomer at the Great New Telescopes of California, Edwin Hubble. In the early 1920s, Hubble aimed the most powerful telescope in the world at that great fuzzy patch in the constellation Andromeda, the Andromeda Nebula. The burning question, still unsettled, was it a cloud of gas inside our Milky Way, or a separate galaxy far beyond it? The scale of the entire universe hung on the answer. Night after night, Hubble photographed Andromeda, and then, on his plates, he found it. A Cepheid variable, a single pulsing star, buried in the haze of Andromeda, keeping its perfect time. He watched it brighten and dim, and he measured its period. Then he used Leavitt's law. The Cepheid's period told him its true brightness. Its faintness in the sky told him how far away it must be to look that dim. And when Hubble worked out the number, it was staggering. Andromeda was far, far outside the Milky Way. Impossibly far. The Andromeda Nebula was not a cloud in our galaxy. It was an entire galaxy of its own, hundreds of billions of stars, separate from the Milky Way, unthinkably distant. In a single measurement, using Leavitt's ruler, Hubble had proved that our Milky Way is not the universe. It's one galaxy among countless others. It's hard to overstate how enormous this was. Overnight, the known universe expanded almost beyond comprehension, from a single galaxy to a cosmos filled with billions of them, stretching across billions of light years. Humanity's home shrank from everything to a single speck in an ocean of galaxies. And it was Leavitt's Cepheids that made the measurement possible. And Hubble wasn't done. Now that he could measure distances to other galaxies, he compared those distances to another clue in their light. A shift in their colors that revealed how fast each galaxy was moving. And he found something even more staggering. The more distant a galaxy was, the faster it was rushing away from us. Everywhere he looked, the galaxies were fleeing, and the farther, the faster, in a clean proportion. This is Hubble's law, and it means the entire universe is expanding. Space itself is stretching, carrying the galaxies apart. An expanding universe. Run that expansion backwards in your mind, and everything was once packed together, which points to a beginning, a moment when it all started expanding. This single insight is the seed of the entire Big Bang Theory, our whole modern picture of cosmic history, and its foundation. The ability to measure those galaxy distances in the first place rested on Henrietta Leavitt's blinking stars. Think about the chain here. A woman measuring photographic plates for 30 cents an hour finds a pattern in pulsing stars. That pattern becomes a cosmic ruler. That ruler proves other galaxies exist, and then proves the universe is expanding, and then underpins the Big Bang. The scale and history of the entire cosmos trace back to Leavitt's patient eye. Her Cepheids became, and remain, the crucial bottom rungs of what astronomers call the cosmic distance ladder, the linked chain of methods we use to measure the universe. Parallax reaches the nearest stars. Cepheids, Leavitt's Cepheids, carry us out to other galaxies. And from there, brighter beacons reach to the very edge of the observable universe. Each rung calibrates the next. Parallax calibrates the Cepheids. The Cepheids calibrate the next method. Exploding stars called type Ia supernovae, bright enough to see across the whole cosmos. Without a solid Cepheid rung in the middle, the entire ladder collapses. Leavitt's law is holding up our measurement of the universe to this very day. Modern astronomers still use Cepheids constantly. When the Hubble Space Telescope, named for Edwin Hubble, set out to pin down the expansion rate of the universe, one of its flagship missions was to measure Cepheids in distant galaxies with unprecedented precision. A century on, Leavitt's blinking stars are still doing frontline science. So the next time you hear about the age of the universe, or the distance to a galaxy, or the expansion of the cosmos, know that underneath it all, quietly holding up the whole edifice, is the work of a deaf, underpaid woman who was never allowed to point a telescope at the sky she measured so well. Which brings us to the hardest part of her story, the recognition she never received, and the honor that arrived just a few years too late. In her own lifetime, Henrietta Leavitt received very little credit for her monumental discovery. Her period-luminosity relation was used by the giants of astronomy, by Hubble, by Shapley, to remake our understanding of the universe. But she remained a computer, measuring plates, her salary modest, her name rarely spoken alongside her discovery. She kept working, quietly and devotedly, through years of ill health. And in 1921, at the age of just 53, Henrietta Leavitt died of cancer. She passed away without ever fully grasping how completely her discovery would transform humanity's view of the cosmos, and without the recognition she so plainly deserved. And then comes the detail that breaks your heart a little. A few years after her death in 1925, a distinguished Swedish mathematician named Gustav Mittag-Leffler decided that Leavitt's work deserved the highest honor in science. He began writing a letter to nominate her for the Nobel Prize. But the Nobel Prize cannot be awarded to the dead. When he made inquiries, Mittag-Leffler learned that Henrietta Leavitt had already been gone for nearly 4 years. The nomination was impossible. The recognition she had earned arrived just too late for her to ever receive it. It's worth sitting with that. One of the foundational discoveries of modern astronomy, the ruler that measured the universe, was made by someone who was underpaid, overlooked, barred from the instruments of her own field, and honored only after it was too late to matter to her. The universe she measured never learned her name while she lived. But history, slowly, has begun to correct itself. Today, astronomers recognize the profound importance of what she found. That period-luminosity relation now has a name that honors its discoverer. It is called Leavitt's Law. Her name finally is attached to her discovery spoken by astronomers around the world. And she has come to stand for something larger. For all the women whose essential contributions to science were minimized, uncredited, or erased. The Harvard computers, and countless others like them, did foundational work while being denied recognition, position, and often their own names on their discoveries. Leavitt is the most luminous example of a vast, quiet injustice. It makes you wonder how much faster science might have advanced, and how many more discoveries we might have if these brilliant minds had been given telescopes instead of just plates, salaries instead of pittances, credit instead of silence. The loss isn't only theirs. And there's a particular poignancy in what Leavitt was denied. She spent her career measuring the light of stars she was rarely permitted to observe directly, analyzing the heavens through photographs, forbidden the eyepiece. The woman who gave us the depth of the universe was kept at arm's length from the sky itself. Yet consider what she accomplished from that constrained corner. Working with nothing but glass plates, a magnifier, and an extraordinary eye, she reached further into the universe than anyone in history. She didn't need the telescope. She had the data and the genius to see the pattern hiding inside it. Sometimes the deepest insight comes not from a bigger instrument, but from a sharper mind. Because that's what her discovery really was. Not a new telescope, not a new technology, but a new idea. The insight that a star's rhythm could reveal its true brightness, and that true brightness could reveal distance. She found a hidden regularity in nature that no one else had seen, and it happened to be the key to the size of everything. It also reminds us how discovery really works. The dramatic moment, Hubble proving other galaxies exist, gets the glory. But it rested entirely on years of patient, boring, uncredited groundwork by someone else. The measurement makes the discovery possible. The person who builds the ruler is as essential as the person who wields it, even if history remembers only one of them. Henrietta Leavitt built the ruler. And every time we measure the distance to a galaxy, every time we speak of the expanding universe, every time we trace cosmic history back toward the Big Bang, we are using her ruler still. Her fingerprints are on our entire modern picture of the cosmos. Let's take a moment to appreciate just how far her simple insight reaches. Leavitt's law let us measure the distance to Andromeda, 2.5 million light-years. It let us establish that the universe is filled with hundreds of billions of galaxies. It underpinned the discovery that the cosmos is expanding, and thus that it had a beginning. It helped us estimate the age of the universe itself, around 14 billion years. It is woven into the measurement of the Hubble constant, the number that describes how fast the universe expands, still one of the most important and hotly debated quantities in all of physics. From blinking stars in a photographic plate to the fundamental parameters of the cosmos. And it all began with a woman patiently comparing dots of light on glass, noticing that the ones that pulsed slower shone brighter. A pattern so simple you could explain it to a child, and so profound it gave us the scale of the universe. That is the strange, beautiful power of careful observation. Henrietta Leavitt's story is, in the end, two stories braided together. One is a triumph, a discovery that reshaped humanity's understanding of its place in the universe. The other is an injustice, a brilliant scientist denied the recognition, position, and honor she had so thoroughly earned. Both are true. Both matter. And we should hold them together. The triumph belongs to all of us now. It's part of how we understand the cosmos. The injustice belongs to history, and to our resolve not to repeat it. The best way to honor Henrietta Leavitt is to make sure the next Henrietta Leavitt gets her telescope, her salary, her name on her discovery, and her recognition while she's still alive to enjoy it. Because there are more of them out there right now. Brilliant minds working in overlooked corners, seeing patterns no one else can see. Leavitt's real legacy isn't only the distance ladder. It's a reminder to look for the genius in the places and the people where we've been trained not to expect it. So let's give Henrietta Swan Leavitt the recognition here that the world was so slow to give her. She was one of the most important astronomers who ever lived. she solved the problem of cosmic distance. She handed humanity the ruler with which we measure the universe. And she did it from a desk with a magnifier for 30 cents an hour. Her Cepheids are still pulsing, out there in the dark, in Andromeda and 1,000 other galaxies. Still keeping perfect time, still telling us how far away they are, still measuring the universe exactly as she taught them to. In a very real sense, Henrietta Leavitt is still measuring the cosmos, every single night. And the universe, she revealed, keeps getting bigger and stranger and more wonderful. More galaxies, more distance, more depth than she could ever have imagined from her little desk at Harvard. She opened a door, and we are still walking through it, into a cosmos vaster than anyone dreamed. There's a kind of immortality in that. Henrietta Leavitt is gone, and was too little honored in her time. But her idea is woven permanently into how humanity understands its home in the cosmos. Every future measurement of the universe's scale carries her insight forward. She measured the universe, and, in doing so, secured her place in it. From a barred door and a stack of glass plates, a deaf, devout, underpaid woman reached across the universe and handed us its measure. That is the story of Henrietta Swan Leavitt, the woman who measured the universe and whom the universe is only now learning to remember. So the next clear night, when you look up at those stars pasted on the dark, remember that we know how far away they are, how deep the universe runs, how many galaxies fill it, because one overlooked woman found a pattern in the pulsing of a star. The sky has a ruler now, and her name is on it. Her law will outlast every telescope, every observatory, every one of us. As long as humans measure the universe, they will use Henrietta Leavitt's discovery. And that is a monument more enduring than any statue, written not in stone, but in the light of the stars. Let's step back and hold the whole arc of it. The problem was ancient and seemingly hopeless. How far away is a star, when all you have is a point of light? Parallax cracked open the nearest few, and then went blind. Beyond it lay the entire universe, unmeasured, its very scale unknown. And the key that unlocked the rest was a special star that keeps perfect time, the Cepheid, and one woman's discovery that its rhythm reveals its true brightness. That single insight, Leavitt's law, turned a blinking star into a cosmic yardstick, and let us step out past the nearby stars into the realm of galaxies. With that yardstick, Hubble proved the nebulae were other galaxies, exploding the universe from one lone galaxy into billions. Then he found them all rushing apart, revealing an expanding cosmos with a beginning. Our entire modern picture, a vast, evolving universe born in a Big Bang, grew from the foundation Leavitt laid. It's a perfect illustration of how science actually builds. Not usually in one heroic flash, but in layers. A patient measurement here, enabling a bold theory there. An overlooked catalog becoming the foundation for a revolution. The person who builds the ruler and the person who measures the cosmos are partners across time, even if they never meet. And it's a reminder of where genius hides. Not only in the famous names and the grand instruments, but in a quiet room of underpaid women squinting at glass plates, one of whom saw, in the blinking of a star, the measure of the whole universe. The next great discovery may be sitting, right now, in some overlooked corner we're not thinking to look. So, the two things to carry from Henrietta Leavitt's story. First, the science, that we can measure the universe at all, that we know its scale and its history, rests on a pattern she found in pulsing stars. Leavitt's law, still holding up the cosmic distance ladder today. And second, the human truth, that brilliance is often overlooked, credit often misplaced, and recognition often too late, and that we owe it to the future to do better. To find the Leavitts among us, and give them the telescope, and the credit, and the honor, while it still means something. Henrietta Swan Leavitt reached across the universe from a desk she wasn't supposed to rise above, and handed all of humanity the ruler with which we measure the stars. She deserves so much more recognition than she got. Let's make sure she gets it now. Her stars are still pulsing. Her ruler is still measuring. Her law still bears her name across the sky. And every time we look out and wonder how far, how big, how old, we are seeing the universe through the eyes of a woman who saw it more clearly than almost anyone, from the humblest of desks. There's a beautiful symmetry to end on. Henrietta Leavitt spent her life measuring the light of distant stars, and now her own light, her discovery, her name, her example, reaches across time to us, undimmed by the century between us. The measurer measured at last, and found to be one of the giants. So look up tonight, and find a pattern in the sky, the way she did. Know that the depth behind those stars, the true, dizzying scale of the universe, was first taken by a woman with a magnifier and an unmatched eye. The cosmos has a measure, and we owe it to Henrietta Leavitt. It's easy to feel small under all those stars, but there's another way to feel it. A single human being, working patiently at an overlooked task, found the key to the size of everything. If that's what one determined mind can do from a desk in the corner, imagine what's still out there to be found. That, in the end, is the gift of stories like Leavitt's. They don't just tell us about the universe, they tell us about ourselves, about what patience and curiosity and a sharp eye can achieve, even against the odds, even unrecognized, even from the humblest of places. The universe rewards those who look closely. Henrietta Leavitt looked closer than almost anyone, and she left the door open behind her. The cosmic distance ladder she anchored is still being climbed, still being extended by astronomers using her Cepheids to measure ever deeper into space and time. Her work isn't a finished monument. It's a living tool, in daily use, 100 years on. So the next time you read that a galaxy is a certain number of light years away, or that the universe is billions of years old, or that space itself is expanding, pause and remember the source. A deaf, devout, underpaid woman comparing blinking dots on glass who found the pattern that let us measure it all. Henrietta Swan Leavitt, say her name, because she measured the universe, and it's long past time the universe remembered her. Her story is a reminder that the history of science is fuller, and stranger, and more unjust, and more inspiring than the tidy version with the few famous names. Behind every great discovery is a web of people, and some of the most important were the ones history tried hardest to forget. Leavitt is proof of that, and proof that we can still remember. We began by asking how far away a star is, a question that seemed impossible. And we end knowing the answer, and the scale of the whole universe with it, because one woman looked at the stars more carefully than anyone thought to. The impossible question, answered from a desk in the corner. That's the story of the woman who measured the universe. A discovery that changed everything, a scientist too long overlooked, and a ruler made of starlight that we still use every night. Henrietta Leavitt's law is written across the whole sky, and now so is her name. Stay curious about the people behind the discoveries, especially the ones you've never heard of. History is full of hidden Henriettas, brilliant minds and overlooked corners, whose fingerprints are all over the world we take for granted. Find them, remember them, they earned it. And stay curious about the sky itself, because the universe is measurable and knowable and unbelievably vast, and every bit of that we owe to people who looked closely and thought hard, like a woman with a magnifier who turned the blinking of a star into the measure of everything. So the next time you see a photo of a distant galaxy, remember how we know how far away it is, because of Henrietta Leavitt. A woman paid 30 cents an hour, kept away from the telescopes, who turned the blinking of a star into a ruler for the entire universe. She didn't just measure the sky, she handed us the yardstick we still use today, and one man used it to become world famous while her name slipped into the footnotes. If Henrietta's story got to you, do two quick things. Subscribe so you don't miss the next forgotten genius we bring back to life. And tell me in the comments, who's a brilliant mind you think history unfairly forgot? Then watch this next, the story of how every single atom in your body was forged inside a dying star. It's right here. I'll see you there.